Welcome to BitCloudTechTalk. In this video, we'll delve into the essential components of Kubernetes architecture, focusing on the controller, pod, and services. In this video, our primary emphasis is on exploring the component and role of pods in efficiently managing containers. Pods act as the fundamental building blocks in Kubernetes, playing a crucial role in organizing and coordinating containerized applications. Think of pods as a convenient wrapper that holds one or more containers. They provide a shared environment for these containers, allowing them to communicate easily and share resources. Before moving to next section, first, we will understand microservices, then role of container in managing microservices, and then we'll focus on all other component which is used to manage pods. Microservices architecture, the way we build software, has evolved, and a popular approach is called microservices architecture. This style offers useful guidelines for creating distributed applications that can adapt to change easily. It's like having building blocks that allow you to design software that can handle a lot of users, recover quickly from issues, and be updated regularly. And these qualities we often need in modern software. Let's understand container. Containers are a modern way of packaging and running these distributed applications. Imagine them as neat, self-contained boxes that hold all the necessary parts of your software. Creating these containers with best practices in mind is crucial, especially as organizations use more and more of them. As the number of containers grows, we need efficient methods and tools to keep track of and manage them. When we talk about being cloud native, it means following modern practices for handling these containers. And one popular tool for this is Kubernetes, which helps manage these containers at a large scale. So, in simpler terms, microservices help us build flexible and resilient software using containers. In Kubernetes, YAML files are used to define and configure resources within the cluster. Let's understand a YAML file main sections first in creating a pod. All YAML file have mainly 4 sections: API version, kind, metadata, and spec. API version specifies the Kubernetes API version used in this configuration. Kind represents the main resources commonly used, such as pod, service, deployment, config map, and persistent volume claim, PVC. Metadata. This section holds metadata pertaining to the resources, such as pod, service, deployment, config map, and PVC, including its name. The metadata definition varies based on the kind. For instance, if the kind is changed to deployment, the metadata definition will be specific to deployment. The spec section plays a crucial role as it describes the desired state of the resource being defined. The purpose of the spec section is to articulate how the Kubernetes resource should be configured and what its characteristics or behavior should be. The exact structure and contents of the spec section depend on the type of resource being defined. The exact structure and contents of the spec section depend on the type of resource being defined. Here are some common elements within the spec section and their purposes. For pods, the spec section includes details about the containers that should run within the pod, volumes, and other configuration settings. It specifies the desired state of the pod, such as which Docker image to use, the command to run, environmental variables, and more. In the case of services, the spec section defines how the service should behave, including the selector that determines which pods the service should target and the ports it should expose. For deployment, the spec section outlines how the desired state of the application should be achieved, including the number of replicas, the template for creating pods, and strategies for updating or rolling back. In config maps, the spec section holds the actual configuration data that should be stored and made available to pods. Let's understand task of controller. In Kubernetes, controllers play a critical role in maintaining the desired state of the system by continuously monitoring and reconciling the actual state with the desired state. Controllers are control loops that manage various resources, ensuring that the declared configurations align with the current state of the cluster. The primary task of controllers is to automate and manage the life cycle of resources. Key tasks performed by controllers in Kubernetes are mainly desired state specification. Controllers work with a desired state specification, usually defined in YAML files or through imperative commands. This specification describes the desired configuration, characteristics, and behavior of the resources. Resource creation and updates. Controllers create and update resources based on the desired state specification. For example, a deployment controller creates and manages the desired number of replicas of a pod. Continuous reconciliation. Controllers run continuous reconciliation loops to ensure that the actual state of the system matches the desired state. This involves detecting any discrepancies and taking corrective actions to bring the system back to the desired state. Rollouts and rollbacks. Controllers handle rollouts and rollbacks of resources. Deployments, for example, gradually update or roll back the replicas of a pod to introduce changes or revert to a previous state without downtime. Scaling. Controllers manage the scaling of resources. For instance, the horizontal pod auto-scaler (HPA) controller adjusts the number of pod replicas based on resource metrics, ensuring optimal utilization. Controllers handle rollouts and rollbacks of resources. Deployments, for example, gradually update or roll back the replicas of a pod to introduce changes or revert to a previous state without downtime. Pod affinity and anti-affinity. Controllers manage the scheduling of pods in relation to each other. Pod affinity and anti-affinity controllers influence the placement of pods based on rules, controlling where pods should or should not co-locate. Garbage collection. Controllers perform garbage collection to remove resources that are no longer needed or have exceeded their specified lifespan. This ensures efficient resource utilization in the cluster. Custom resource definitions. Controllers can be extended to manage custom resources using custom resource definitions. Custom controllers are created to handle the life cycle of these custom resources. Ensuring high availability. Controllers contribute to the high availability of applications and services by maintaining the specified number of replicas, handling node failures, and rescheduling pods as needed. Integration with core Kubernetes components. Controllers integrate with core Kubernetes components like the API server, etcd, and kubelet to monitor and manipulate resources. Common examples of controllers in Kubernetes include deployment controllers, stateful set controllers, replica set controllers, daemon set controllers, and more. Each controller is designed to manage specific types of resources and enforce their desired state within the cluster. These examples provide a glimpse into how controllers are defined in Kubernetes YAML files to manage different types of resources. Each controller has specific characteristics and behaviors tailored to the requirements of the managed resources. A deployment controller manages the deployment and scaling of applications. This example defines a deployment named Nginx deployment that ensures there are always 3 replicas of the Nginx pod running. A stateful set controller is used to manage stateful applications with unique network identifiers. This example creates a stateful set named web that manages 3 replicas of the Nginx pod with unique network identifiers. A daemon set controller ensures that a specific pod runs on all nodes in the cluster. This example creates a daemon set named Fluent Elasticsearch that ensures a pod with the specified image runs on every node in the cluster. A replica set controller ensures that a specified number of replicas of a pod are running. This example defines a replica set named frontend that maintains 3 replicas of the Nginx pod. Let's understand pods and its underlying architecture. Pod is the smallest and simplest unit in the Kubernetes object model that can be created, deployed, and managed. A pod represents a running process in a cluster. Pods are a fundamental building block in Kubernetes, and several unique attributes make them crucial for orchestrating containerized applications. Atomic unit of scheduling. Pods are the smallest deployable units in Kubernetes and serve as the atomic unit of scheduling. The Kubernetes scheduler schedules pods to run on nodes based on resource availability and constraints. Collocation of containers. Pods enable the collocation of containers within the same logical unit. Containers within a pod share the same network namespace, allowing them to communicate easily and efficiently with each other using localhost. Shared storage and volumes. Containers within a pod share the same storage volumes. This enables data sharing among containers in the same pod and facilitates communication through shared storage. Single IP address. Pods have a single IP address assigned to them. All containers within the pod share this IP address and communicate over the same network. This simplifies networking and allows containers to easily discover and connect to each other. Inter-process communication. Containers within a pod can use inter-process communication mechanisms for high-performance interactions. This allows containers to efficiently exchange data and signals. Life cycle and termination. Pods have their own life cycle. When a pod is created, the containers within it are started simultaneously, and when the pod is terminated, all of its containers are stopped. This ensures consistency in the life cycle of containers within the same pod. Resource sharing. Pods allow containers to share resources, such as CPU and memory limits. Resource constraints specified at the pod level are shared among all containers within the pod. Labels and selectors. Pods can be labeled with key-value pairs, and these labels can be used by selectors for grouping and identifying pods. Labels and selectors are powerful for organizing and managing pods within a cluster. Flexibility and composition. Pods provide flexibility in composing containers that need to work together. They allow bundling of related containers into a single unit, ensuring that these containers are scheduled and run together. Pod anti-affinity and affinity. Kubernetes allows the specification of rules for pod anti-affinity and affinity, influencing how pods are scheduled in relation to each other. This helps in controlling the distribution of pods across nodes in the cluster. Init containers. Pods can have init containers that run before the main containers start. Init containers are useful for performing tasks such as pre-initialization or setup that is required before the main application. Containers start. Understanding above attributes highlights the significance of pods in managing containers efficiently within Kubernetes. They provide a cohesive and flexible abstraction layer, allowing for effective orchestration and coordination of containerized applications. In this section, let's understand services. In Kubernetes, a service is an abstraction that defines a logical set of pods and a policy for accessing them. Services enable communication and discovery between different parts of an application by providing a stable endpoint. There are many types of services like Cluster IP Service, The cluster IP service type in Kubernetes exposes a set of pods internally within the cluster. It provides a single, stable network endpoint that other applications within the cluster can use to communicate with the selected pods. This service type is often used for internal communication between different components of an application. Node port service. The node port service type exposes a set of pods to the outside world by assigning each node in the cluster a specific port. This allows external access to the selected pods using the node's IP address and the assigned port. While node port is a straightforward way to expose services externally, it may not be suitable for production environments due to potential security and scalability considerations. Load balancer service. The load balancer service type in Kubernetes is designed to expose a set of pods externally using a cloud provider's load balancer. It automatically provisions a load balancer and directs external traffic to the selected pods. This service type is suitable for production environments where external users or systems need to access the services provided by the selected pods. It ensures high availability and even distribution of traffic. External named service. The external named service type in Kubernetes acts as a simple alias that redirects a service to a predefined external DNS name. Instead of exposing pods, it allows a Kubernetes service to act as a reference to an external service hosted outside the cluster. This can be useful for integrating with external services or transitioning between different environments without modifying application configurations. These different service types in Kubernetes provide flexibility and options for exposing and accessing applications based on specific use cases, whether for internal communication, external access, or integration with external services. This example creates a service named MyService that routes traffic to pods with the label app, MyApp on port 8080. The service itself will be accessible within the cluster on port 80. Let's see some examples which illustrate different types of services in Kubernetes, each serving a specific purpose in exposing and networking pods within the cluster or externally. In this example, the MyCluster IP service named service exposes pods with the label app NGINX as a single, stable network endpoint within the cluster. The MyNode port service named service exposes pods with the label app NGINX to the outside world using a specific port on each node. Here, service named MyLoad Balancer exposes pods with the label app NGINX externally using a cloud provider's load balancer. In this example, the MyExternal name service redirects to a predefined external DNS name example.com. Let's consider a use case where you have a microservices-based application composed of multiple services, and you want to expose these services using different Kubernetes service types based on specific requirements. Use case: online retail application. In an online retail application, you have microservices responsible for different functionalities. In this use case, each service is exposed using an appropriate Kubernetes service type based on its requirements. The cluster IP service keeps internal communication between microservices. The node port service allows external access to the web frontend. The load balancer service enables external access to the checkout service with a cloud provider's load balancer. And the external name service redirects to an external payment gateway.